So it's a great pleasure for me to introduce Professor Marco Diana from the University of degli Studi di Sassari, because Marco Diana has been my first mentor before I left Sardinia, my island, and Marcos Island, to go to the States. So from Marco, I've learned a single unit recording in rats. Remember, in the basement of il Palazzo delle Scienze dell'Università di Cagliari. So we have a lot of history. I have a lot of history with Marco, and it's a pleasure really to have him here. Marco is an expert in drug of addiction and specifically the effects of the dopaminergic system. For many years, he has worked on animal models, on electrophysiological, using physiological methods, and now is going to more fMRI and
transcranial magnetic stimulation.
Exactly. So we will know more about what are the results, what is the state of the art nowadays on what is the brain telling us after we get some cocaine or some exciting drugs. So thank you, Marco, for being here, and looking forward to your lecture.
Thank you. I'm really delighted to be here, especially to see so many young neuroscience enthusiasts. I hope that I will not be too esoteric with the transcranial magnetic stimulation, but I will try to render this thing digestible enough. We employ this new technology hoping to provide a different therapeutic approach to drug addiction. As you certainly all know, drug addiction is an increasing phenomenon, is a disease that is reaching the status of social disease. And for your information, I will tell you that Barcelona is the city in Europe in which the highest amount of cocaine are found in the sewage system. These are data of the European Monitoring Center in Lisbon. And as I said, it goes beyond the neurobiology of drug addiction. It goes beyond rats self-administering cocaine or morphine or opiates in general, but is affecting all layers of society, even our layer. Our layer, I mean scientists which have free access to drugs. Some of them, sometimes, they get hooked and they become addicts. So the addiction problem is not a problem that relates only to homeless people or people that sleeps under the bridges, but it affects everybody, every single individual, men, women, children, everybody. What I will do, or what I would like to do with you today, is to talk about the neurobiology first, and then the approach with transcranial magnetic stimulation to evaluate if this is a good method, or at least is a better method than the previous ones. The previous ones are drugs, again, pharmacology. We treat addicts with drugs. And many times, it happens that one single molecule is not enough to govern the behavior of the addict. Therefore, you are forced to administer several drugs at the same time. This poses a fundamental problem. While the therapeutic effects of the various molecules are probably kept, the toxicological effects are magnified. So you have individuals which literally lose their cognitive functions. You heard from the previous speakers, we were talking about decision making and working memory, and all these functions are deranged in the brain of the addict. This is the fundamental reason by which we are investigating deeply transcranial magnetic stimulation to evaluate the possibility of treating patients with this method, which is an electrophysiological method. I will go into more details as the lecture goes on. The lecture is divided in three main parts. The first part will describe classic now findings in rodents mostly, which converge on the hypothesis that we published several years ago, stating that the addicted brain is a brain in which the dopamine system works less, tonically less than normal individuals. These were the initial observations, and we know that since we are treating a human disease, and more or less, or in general, we are interested in human therapies, not rodent therapies, we crossed this evidence with human evidence. So if it is true that the rodent brain is poor in dopamine transmission, is this also true in the human brain? You all know certainly that we can nowadays investigate the in vivo brain with PET scanning, fMRI, and all these kind of visual imaging methods. And the answer is yes. Even the human brain shows signs of hypodopaminergic functioning. Given this, the third part will focus on the transcranial magnetic stimulation method, the fundamentals. Where is this working? Because I don't want you to leave this room thinking that we do transcranial magnetic stimulation simply because it's fashionable and is very nice and is very new. But we employ transcranial magnetic stimulation with the specific aim of stimulating through the prefrontal cortex, and I will show you the pathways, the dopamine system that is working less in addicts. If you have any question, just raise your hand and I'll be happy to answer if I can, of course. So, let's start. What is addiction? This is George Cook's work. He is my favorite theorist. He has done throughout the years a number of classification of the disease. So, I won't go through all the details here, but I want you to focus on this part and this one. Binge intoxication means the initial intake of the drug. It is frequently called the honeymoon of the addict. He loves this period. Cocaine is fantastic. It's anxiolytic. It makes you happy. It makes you working. It's just fantastic. We know, though, that this phase doesn't last long. And with variable time, at one point, it begins to realize that his life is plunging. Lots of money, efficiency at work doesn't work anymore, family problems, kids, and many other things. So he enters in a phase in which he thinks that it's much better to stop. But this is not easy. And we enter this phase, the withdrawal negative phase. It is different from this one because, oops, It is different from this one because of the positive and negative reinforcement. So at the beginning, it takes the drug, but because when it takes the drug, it feels better. To the end, negative reinforcement takes place. So you take the drug because if you take the drug, you can avoid the negative effect of withdrawal. Although it's a common popular knowledge that psychostimulants don't give withdrawal, don't believe that. Withdrawal, cocaine withdrawal, is a terrible phase. Although it doesn't shake, it doesn't have diarrhea, it doesn't have the signs of opiate withdrawal, cocaine withdrawal produces anhedonia, depression, dysphoria, and many other things which fuel the drug seeking that occurs inevitably. And this is one of the main problems, preventing relapses. So after this, let's say, behavioral framework, what is actually happening in the brain of an addict? There are, as you can see from this slide, many areas that are involved in the chronic effects of drugs of abuse. You can see here the amygdala, which puts an emotional stamp on the experience, the nucleus of the stria terminalis, and the nucleus accumbens, just to name a few. But all those that you see, prefrontal cortex, orbitofrontal cortex, dorsal striatum for habits, and many, many areas. We need, of course, if we are seeking efficacy in therapeutics, we need to identify a system, or better, even a neurotransmitter, and try to target this system to evaluate the possibility that it will be helpful therapeutic. And here is the system. As you can see here, the red things here are the cell bodies of the dopamine neurons. I'm sure that everyone here is familiar with the dopamine system, the pleasure neurotransmitter. You can find in YouTube, even in newborn, I think. That dopamine mediates pleasure. It is a first approximation. For us, it's not exactly that way, but these are the neurons. They have their cell bodies in the ventral part of the mesencephalon, and they project to the neostriatum, to the prefrontal cortex, and the VTA, which is the medial part of the mesencephalon, projects to the nucleus accumbens. You can see here histological sections. VTA projects here, while substantia nigra projects to the neostriatum. This is the system with which I fell in love many years ago, and dopamine, to be a lover, is a good choice because she's obviously female and she doesn't even talk. My wife is not jealous and we are all perfectly set. This drawing represents the terminal part. The blue thing here is a medium spiny neuron. The medium spiny neuron occupies roughly 99% of the nucleus accumbens. It receives two fundamental projections. One is glutamate, which is this one, the yellow guy, which hangs, as you can see, on the head of the spines. We'll see spines also, dendritic spines in a bit. And these are coming from the entire cortical mantle. So from the prefrontal cortex, thalamus, they bring glutamate here. On the contrary, the dopamine terminals, they land mostly on the neck of the spine. These three things here are called the synaptic triad of the nucleus accumbens. So when we want to study pharmacology, we have to integrate all these three things. And we'll see throughout the lecture that we will measure the activity of these neurons. We will see studies depicting the action of drugs on the dendritic spines, and so on and so forth. So this is a Anna was probably still in the lab in these days, but she was
1993
ready to leave
maybe.
to go to California. But this is the very first evidence that led to the final concept of hypodopaminergic states. These are examples: firing rate histograms, single cell, antidromically activated from the nucleus accumbens, and this is a controlled dopamine neuron, and this is a dopamine neuron during ethanol withdrawal. It's easy to see that this guy is firing much less than this one. So the activity, the neuronal, spontaneous neuronal activity of these cells projecting to the shell of the nucleus accumbens, they simply fire less tonically once the individual is under withdrawal. Once it's been taking ethanol chronically and you suspend ethanol, it goes into withdrawal, and it manifests this with a lower firing activity. If you now go to the nucleus accumbens with the dialysis method, with the microdialysis method to measure synaptic dopamine, in that synapse that I showed you just in the previous slide, this is what you see. This is the last ethanol administration, and then you stop, and you see that even dopamine release goes down and remains down. So we have here two pieces of evidence. Spontaneous firing rate is lower in ethanol withdrawal, and dopamine release in the terminal region, in the nucleus accumbens, is also reduced. That says that the whole neuron is firing less than normal. So, is this true only for ethanol, or we may generalize this to other drugs of abuse? Here are opiates. This is morphine. You know, let me spend 2 words for opiates, because also regarding opiates, we are in a crisis. I don't know if there is anyone from the US here. The opioid crisis.
We have one representative, Lucas. You
Oh,
can
good.
tell him.
So you know that even the Trump administration has poured a few billions of dollars to save these opioid pandemics. The worst pandemic in opioid abuse since history. In 2016, 62,000 American citizens have died of opioid overdose. This is attributed in part to some malpractice, but in part is also attributed to the fact that the drug smugglers are now synthesizing fentanyl and its derivatives. So they don't do any more phencyclidine and methamphetamines and ice and this and that and MNDA and all those junk that they used to do. They also synthesize fentanyl. Fentanyl and its derivatives, which are very easy to synthesize in a lab, in any place, are molecules that are 5,000 times more potent than morphine. So it's very easy to miss the dose. 62,000 people died in 2016. What you see here in rodents, well, before this pandemic, but I felt obliged to communicate you this thing, is the same thing that we have seen for ethanol-dependent rats. These are morphine-dependent, and these are controls. As you can see here, the firing rate of these neurons are almost silent. And since we keep them antidromic control, we can see that they are not dead, but they are simply silent. So this is the second molecule, totally different from ethanol, as we all know, that induces the same thing, an hypofunctioning of the dopamine system. Let's move to another more popular and more diffuse, especially in the young part of the population. I'm talking about cannabinoids. Specifically, I'm talking about delta-9 tetrahydrocannabinol, the main psychoactive ingredient of the hemp plant. This is an experiment that was published again a long time ago. These are the control neurons. These are the same dopamine neurons under spontaneous withdrawal. Spontaneous withdrawal means that these rodents, these rats, they took cannabinoids for 6 days. And then 24 hours after the last administration, you record from them. And you see that is significantly less than this one. To cross-check if this is really related to a spontaneous withdrawal, we did a pharmacologically precipitated withdrawal. What it means is that the rat takes delta-9 THC, and an hour later you administer the drug that was called rimonabant. It's a drug by Sanofi, which was introduced in the market for obesity control, for food intake, because it reduces food intake. Then it was removed because there were 2 or 3 suicides, and that now is not in the market anymore since 10 years ago. But in those days, rimonabant, it was called SR1418 something. As you can see, if you administer rimonabant, you have even a further decrease in firing. So the tonic activity of dopamine neurons is even less and has become dependent on the administration of the exogenous drug. At this point, we have 3 classes, 3 pharmacological classes of drugs of abuse, which when administered chronically and then suspended, they induce an hypofunctioning of the dopamine system. Is this now related to other behavioral manifestations still in rodents? For instance, when you are under ethanol withdrawal, you observe a decreased brain reward, as you might expect. If dopamine is important in reward, when dopamine is low, this reward must be less. It is intuitive. How is this done? This is done with a method called the intracranial self-stimulation, which I assume you all know, but in brief, you put an electrode into the medial forebrain bundle, into the part of the system that goes to the forebrain. And then you train the animal to self-administer current. It stems from the classic experiments of Olds and Milner, when they described the pleasure centers in the brain. So as the rat learns to stimulate the medial forebrain bundle, when it reaches enough current, then it keeps stimulating. And this is what happens in the normal control rat. It requires a certain amount of current. If you have an ethanol withdrawn rat, you can see that the behavior is preserved, but it requires more current than before. This is very consistent with what I told you just a minute ago. The neuron, the dopamine neuron, is hypofunctioning, is probably hyperpolarized. So you give him more current, it depolarizes it and keeps the behavior going. So this is very consistent with the notion that the medial forebrain bundle and thus dopamine is directly or indirectly mediating this effect. Now, after this pharmacological appetizer, we have some anatomy. And anatomy is important because it tells us the structure of the brain. It tells us about modifications, structural modifications, structural plasticity there. So you can measure before and after and modulate the action of drugs even on the real structure of the neuron. Confocal microscopy, why? Because confocal microscopy gives us a three-dimensional, the possibility of a three-dimensional reconstruction without going so focused as the EM does, the electron microscope does. So I can see cells, I can see networks, I can immunocytochemically mark them and get impressions of what is going on. You certainly know that the confocal is given by this trick that the machine does, so it moves the focal plane and then it puts everything on a single slice, and you have something that was previously impossible. No? We can also mark these cells before we do the anatomical analysis with immunocytochemical markers, and so identify exactly which cells we are studying, we are looking for. Okay? Here you find, this is the mesencephalon, this is the mesencephalon, so substantia nigra and DTA, and you take them from here, and here is the nucleus accumbens. So we are taking the cell body and the terminal region of the dopamine neurons to study under morphine withdrawal conditions, so opiate conditions. We do this with TH positive neurons. TH stands for tyrosine hydroxylase, which is the step limiting enzyme in dopamine neurons. And as you can see, you can reconstruct entirely the neuron and measure neuronal morphology if it is increased, decreased, modified, and blah, blah, blah. Okay? Here's what you do. You see, you slice the confocal microscope that does this. It does several slices, one each micron, and then you reconstruct the neuron. You check for autofluorescence down here, and then you can be sure that those neurons are really TH positive cells. In those cells, you do your counts. These are 4 groups. This is all published material if you are interested in further details. But the fat arrow here indicates the TH positive, which can be seen here also. This is a control example. This is a chronic example. Chronic means that the animal is sacrificed when morphine is on board, is not withdrawn. Morphine is on board while it gets decapitated, okay? And these are the two withdrawal conditions, spontaneous withdrawal and naloxone precipitated withdrawal. It's fairly easy to see that only the fat arrows are indicating TH positive neurons. So if you compare, it's easy to see that these two are similar, while these two are very different. And the counts, oh, I'm sorry. No, I thought I had the counts. That's okay. These two conditions, the morphine withdrawn rats have a smaller VTA TH positive neuron. So this piece of information goes to add to the lower spontaneous activity, and adds in the sense that you are observing a structural phenomenon. The neuron is not only functionally different than the control, but it's also structurally different. So there are problems in the structure, and we will see this further down. This is an example of what happens in the nucleus accumbens. So far I described you the results of the VTA, TH containing neurons. We are now heading to the nucleus accumbens, so to the terminal region, so to the dopaminoceptive neuron, where dopamine spreads into the synapse, into the net of the spine of these neurons. These are the neurons, medium spiny neurons, Golgi stained. The green stuff are the TH positive fibers, and the purple thing is the PSD95. The PSD95 are a bunch of proteins that sit on the head of the spine, and they dock the NMDA receptor and the AMPA receptor. So we use that as a proxy of the glutamate transmission. Here is the first example in the shell of the nucleus accumbens. These are medium spiny neurons. The groups are, as I said before, control, chronic, spontaneous withdrawal, naloxone-induced withdrawal. You can see here the amount of spines, these little blebs that you see next to the dendritic, especially the second order dendritic trance. And here you can see more or less the same quantity. If you look here, for instance, the dendritic trunk is almost completely smooth. So the spines have disappeared. This is a vectorial analysis simply to emphasize the possibilities of this method. You can magnify this without losing proportions among the various elements, and you can do your spine counts as accurately as possible. And here are the final counts. You see that in first order dendritic trunks, you don't see any change across the various pharmacologically induced conditions. while you do see them during both withdrawal conditions. Curiously enough, dopamine transmission projects almost exclusively on second-order dendritic trance. And there are data in the literature in Parkinson's disease models, 6-hydroxydopamine, NPTP, and all the various toxins employed, which suggest that if you have a low dopamine tone, the spines, they simply die. And the spine has to be considered more than a simple decorative appendage of the neuron, but has to be seen mostly as a computational unit, because it has to integrate dopamine and glutamate and the various other things, so it decides if the depolarization or hyperpolarization goes to the dendritic trunk and eventually to the cell body.
Marco, one question on the, if you go back, what are these three different conditions you list there?
Control,
That I got, but the other three.
chronic, morphine. 14 days of escalating morphine doses, twice a day. It reaches, if I remember correctly, around 140 milligrams a day. It should mimic more than other methods like the mini pumps and all these things. It should mimic the human condition, because addicts, they do 10 today, tomorrow will be 20, if they can. But so this is chronic, and it means that the animal gets sacrificed when morphine is on board. Okay, so it has still morphine. And here, this is spontaneous withdrawal.
Right, so that's what you explained earlier?
Yes, spontaneous withdrawal, the animal gets sacrificed 24 hours after the last administration. Morphine is not on board anymore. And this one is 1 hour after. Morphine is on board, but the dopamine receptor is blocked by naloxone.
So it also means as an addict, they will be cycling between these two states, right? So
Between these two.
Exactly.
Yes. Yes, they are cycling exactly between these two states. In my view, they are most of the time in this state, and then they seek to go back to this.
Exactly.
But this is a very important point. One will go to the clinical part, because when we treat people, we need people that come to us and says, I need help. If you don't have that, you don't have a patient, and you don't have work. And not everybody is aware of the fact that he's in trouble and is treatment seeker. There are many studies made on cocaine addicts. So the criteria fulfill the diagnosis of cocaine addiction, but they are not seeking treatment. My friend Diana Martinez at Columbia University, she pays the patient to stay in the hospital for 15 days, cocaine independent. You stay with me, and I will pay you day by day if you give me 3 hours of your time for me to give my tests, like PET scanning, number of receptors, and decision-making tests and working memory. We are not allowed to do this in Italy.
Right, okay.
So, should you
It's clear,
keep going? Okay. And this is back to cannabinoids. The green spots that you see here are indicating synapses. So the juxtaposition between a TH positive terminal and a dendritic spot. Here is a control in the core, and you see how many green spots you see. This is a control in the shell, which is the medial part. And this is the shell after spontaneous withdrawal from THC. Even in this case, it's much easy to see that there are less synaptic contacts. This also results in some functional consequence. And the functional, this is a computational analysis. I heard this morning talking about computation. We made a computational model of the medium spine neuron, including in these dopamine receptors and the physiological parameters. These are very curious neurons. They live in two states. This one, which is called the down state, and this one, which is called the up state. So when the neuron goes into the up state, it's able to release action potentials. But in general, these are neurons that are kept most of the time very silent. Here is the control guy, and here is the guy after THC, cannabinoid withdrawal. It's easy, again, to see that while this one is firing 5, 6 action potentials for every up state, this one is firing only 2. So we can add another piece to the puzzle, to the initial puzzle. This is not only the dopamine neuron that is firing less and releasing less, but it's also the dopaminoceptive neuron, which is this one, the medium spiny neuron, that is working less and showing structural abnormalities like spine loss, lack of functionality, and combines with the presynaptic terminal. So it's dopamine together with this dopaminoceptive side that are working less in various animal models of addiction. That goes to the final conclusion that was taken from this and other, which in the normal state you see a TH positive neuron connected with the medium spine neuron, while in the normal state this is what happens. In the addicted state, it shrinks. You can see it better if I go back. See, normal state, addicted state, normal state, addicted state. The neurons are shrunk, and this is accompanied by lower firing rate, lower release of dopamine in the terminal region.
But in this case, only the soma shrunk, right? Given the cell body itself, the core.
Yes.
The processes didn't seem to change a lot.
The what?
The dendrite and the axon. The processes coming out of the cell body didn't change too much. Or did I miss it?
No, you didn't miss it. That was only for the cell body in the VTA. Here, there is a change. There is a change in the dopamine transporter, but I don't have all this data. It will take 6 hours. But we published a paper in PNAS in 2014 in ethanol withdrawal drugs describing TH and that amount. That doesn't change. TH does. And is reduced in the withdrawal animals.
Do you have evidence that shows the dopamine are shrinking in people, human addicts?
No. I don't think this is, in humans, I think this is beyond the power of resolution of PET scanning, but I don't see any method to measure. Oh, autopsy.
Yeah.
Autopsy, not easy. No, but I don't know. I don't know. No. This is in the dendritic trunk, in the medium spiny neuron, and this is in the normal state. When you go to the addicted state, you see that the spines apirin, making the dendritic trunk smoother, so reducing the possibility of synaptic contact. Now, if any one of you is interested into more details, this is the original review, the original hypothesis, in which you will find many more details. At this point, I should go to the human brain. Is there any question? Right answer? Everybody
You go to the human brain now with this hypothesis in mind.
Exactly.
Okay. So
I'm going to the human brain to verify if what I concluded in rodents, and the conclusion is the dopamine system is hypofunction. This is in rodents. Let's see if in the literature that is available we can confirm this in humans, because for the very simple reason that we are interested in addiction as a disease of the human race. That's
So, with respect to the red data, so you show that you lose the dendritic spines in a few hours, right?
yes, even less than a few hours.
That was my question. So what's exactly the time course of this reduction?
Okay, in opiates, and that was a long discussion with the reviewers of the papers in those days. Yes, it is very fast.
Minutes?
Surprisingly
Hours?
fast. No, minutes.
It's almost like binary, it's really like a collapse. Then it really goes from one state, like up and down states if you want, but then for your spines, it just collapse in a very short period of time.
The
Or
short
it's a
period of
gradual
time.
decline in a certain time zone.
No, it's a sharp decline that occurs in 30 minutes. As you give naloxone, 30 minutes later, you analyze the brain, and the spines are already down. And that was part of a long discussion between us and the reviewers regarding the time course of the proteins. Acting
On the
is
spines.
important on the spine apparatus, the PSD95, there are a number of things. So you go, after all, in discussing the turnover of proteins. But
I was thinking, when you were showing the data, I was thinking about what might be the mechanism of this loss of spines and so on. And first I was thinking they're being down-regulated by gene expression, but what you're saying now would indicate more that once they lose their afferents, their bombardment from the sick dopamine cells, once they lose that, they are simply collapsing. In other words, the spine is being maintained by activity. Is that the reasonable?
that's one of the things, yes. Dopamine, in one word, this is I would say, just a second, shared information. Dopamine has a trophic role on the health of the spine. Gloria Meredith has done some work on this stuff, and Gordon Arbuthnot, when he was in Edinburgh, and they all share this vision. Dopamine is trophic. If you deprive dopamine, the spine just disappears. Yes, please.
So how long does it take if you stop administering to recover?
Oh, to recover what?
Well, if the
Spines.
size or the properties.
Oh, thank you for reminding me that there are still some more work to be done. We did it for something. The firing rate in opiate-dependent rats recovers to normal levels at 14 days. But even if the firing rate is back to normal, if you look at it, if you now administer morphine, the X-dependent rat will respond much more than the control rat. We did this for morphine, and it's published, again, 98, I don't remember. And alcohol dependent. It goes back, alcohol dependent, firing rate goes back in 5 days, 7 days, something like this. We didn't do it for all the others. Again, thank you for reminding me that I still have something to do.
Yeah, because you can now recognize what are the, let's say, downsides of addiction, then
Exactly. That's it, the point. Please.
And the spines, like the number of spines, the shape of the cells, also get recovered in this amount of time.
Okay, yes. Here I can answer yes. At least in ethanol withdrawn rats. We have a paper in press now in Journal of Neuroscience, which is the follow-up of the PNAS paper in 2014, in which we have described the loss of spines and various types, because we are not even going further into the details. There are mushroom spines, the big head spines, which somebody likes to call the memory spines. And then there are long thin spines, and somebody again calls them the learning spines. Kazai in Japan, experts on these things, they do glutamate uncaging and all those fancy experiments, okay? Now we are publishing the second part of that work, and if you administer L-DOPA to those guys, to the ethanol-deprived animals, you turn back to spines, normal configuration of spines, LTD, which that is another point. The ethanol withdrawn rat doesn't show you LTD, suggesting that this is not a problem only of dopamine, and is not a problem of the spines, but is a problem of learning. If you don't have spines and you don't have dopamine, you simply don't learn at the cellular level. If you now give back, you provide L-DOPA to boost the dopamine transmission, then the LTD is apparent again. Okay? Another question, please.
This is about the withdrawal. How do you compare it between rodents and humans? Because the major factor in humans to feed the cycle is the ability to take the drug, which is absent in rodent experiments.
Of course, to make a direct comparison is not possible, but in humans you reason differently. How do you reason? As I was saying or anticipating earlier, you have an addict and he comes to you, okay? And he says, I'm seeking treatment. Then the clinician first makes the diagnosis, and included in the diagnosis knows when the last time he took the drug. And then he does his experiments. This is what Nora Volkov and Diana Martinez and all those people that they do these things have done. Okay? So we'll go fast now. As I said, you can, with due approximations, you can do similar studies in humans. And one of the ways, one of the methods you can employ is the positron emission tomography. In brief, what is this? You give a radio drug, a radioactive drug, you inject the drug, this drug sticks to one of these things, or multiple. You can study the dopamine transporter, you use a cocaine analog, radioactive, and it will go to mark and to label your dopamine transporter proteins, so in the terminals of dopamine neurons. Or you can do dopamine receptors. You can employ iodosulfuride, for instance, which is another radio tracer, and study this. You can also study metabolism with 6-deoxyglucose, which is another radioactive drug, and study which regions are responding more or less depending on the treatment you are applying. After all, what are you doing? You are doing this. You are studying the dopamine transmission, the presynaptic terminal, the amount of dopamine, the number of receptors. The good news here is that this is a living human brain. This is not a rat, this is not a mouse, it is not a marmoset, it is not a kangaroo, I mean, it's a human being, and this is very important. So here is the general and one of the first considerations about dopamine receptors. Here is a normal subject. Here is a cocaine abuser. 1 month post. Remember the question? 1 month post. What do you see? There is no red, virtually. Red is indicating, higher binding. Higher binding. Okay, so the radioactive molecule is sitting here. Here there is nothing sitting. Okay? Presumably, these are dopamine receptors lost. Where did they go? I don't know. And not even Nora knows. But they are not there. Okay? If you are patient enough and wait 4 months, then you begin to see a little reddish again. What is this saying? This is saying that protein synthesis is keeping pace. You eliminate cocaine and dopamine receptors slowly. They are reacquiring their place in the ventral striatum. Okay? So, this is also another way to say that the dopamine transmission is working less in these guys, no? A normal guy has 10 receptors, this one has 1. There is no way that dopamine can transmit its own signal. Here is another evidence. This is Diana Martinez now, to see that it's not only a group of people, but these are results that have been contrasted and are now shared. Okay? You can administer amphetamine. Why would you do that? You do that to increase the endogenous release of dopamine. Now, I'm now entering a sort of a detail for pharmacologists. The pharmacologist, I am a pharmacologist and I know I have many sins. But pharmacologist, one of the problems is the so-called denervation supersensitivity hypothesis. What was that? And it stemmed from binding studies in the 70s mostly. They got the idea that when you deprive a transmission from the presynaptic terminal, dopamine, for instance, dopamine, you do 6-hydroxydopamine, and then you measure receptors in the striatum. Receptors went up. To explain this thing, they said because there is a denervation supersensitivity. You don't have the neurotransmitter. So the receptors, they adapt and they increase their number to compensate for the lack of function. See? When these results came out, you are seeing here the opposite. You are seeing that the receptors are going down. So the pharmacologist couldn't believe this. This is impossible that there are fewer dopamine receptors. There must be more dopamine receptors. So this experiment is done to kill that hypothesis, okay? So what did she do? She did the cocaine dependent. She found less dopamine receptors, and she said, if now I administer cocaine and I release dopamine, these receptors, they must change, but they did not. So even the pharmacologists are now quiet, and they take the thing that the hypodopamine function can coexist with less dopamine receptors in the postsynaptic side. Did I explain this? Okay.
So is that specific now also for the receptor system we look at?
Yeah.
Because the supersensitivity was seen as a generic system for any
Exactly,
transmitter.
too generally.
But now is the alternative to say it will depend on which transmitter system you look at. Some down-regulate, some up-regulate, others don't care.
Mhm.
So what's the replacement? To kill it is one thing, right? But now we want to hear the alternative.
Yeah, but I don't have it.
So what's the evidence for?
The only system that I know is dopamine. And I know in detail this one. But if you will ask me about serotonin, I will not know.
But
Perhaps
for
somebody
dopamine-
else does.
Or what about the D1 receptors?
Say it again?
The D1 receptors, so this is D2, D3, and the previous
Yeah,
one was D2.
it was never measured. There is
Exactly.
no a nice ligand for the D1. Now the Canadian, Isabelle Boileau, and Alain Daguerre, and Strafella, they are pulling out a D3 selective
Right.
thing. But D1, to my knowledge, has never been developed for human use.
I can help a little bit on the innovation sensitivity.
Yeah.
Because
Tell him.
there is now a genre of research. It calls itself neuronal homeostasis, and it's various ways in which cells adapt to the loss or increase of afferents. And the innovation sensitivity is simply one of several mechanisms. So therefore, I would suspect that different systems will show very different patterns. And here you presumably have shown us a system where innovation sensitivity is not the operative homeostasis mechanism, but
No.
maybe some others.
Exactly.
So I think that's
Exactly.
I think it's not the problem.
But on top of that, it will then again also depend on what the specific receptor does.
Yes.
Right?
Yes.
Because homeostasis will depend on also postsynaptic properties.
So this is
And
neuronal
these-
homeostasis at the single cell level, not homeostasis for the system. That's just the
No, I
single cell.
understand,
Yeah,
I got
okay,
that.
yeah.
But the point is that now you have a much more heterogeneous set of responses, right? This is then what we have to try to figure out.
Yeah.
Where across the 5 types of dopamine receptors, that all get at various distributions on different cell types, you can then expect, let's say, a uniform response.
Yeah.
You gotta tell us that, Marco.
What?
You gotta tell us that.
Okay, if I will live long enough, I will do my best.
We'll try to keep you alive as long as possible.
Okay. So, that was the story in brief.
And now the long version.
No. Now we'll slip to the end, at least of this second part. Is anyone collapsing after all this? No, not yet? Okay, good. Okay, now this is simply to say that the lower dopamine receptors and the low dopamine transmission or hypodopaminergic state does not apply only to cocaine. But as you can see here, alcohol dependence is another one of those. And opiate we spoke already about, and Diana has demonstrated and has worked at length with alcoholics. So the informations we are taking as general information of lowering of the dopamine receptors functioning in general applies not only to cocaine or psychostimulants, but also to alcoholics and alcohol dependence in general. This is another example of what happens. These are control subjects, still PET scanning, so the red here indicates many receptors. To one group you give placebo, and to the other group you give methylphenidate. As you know, methylphenidate is an amphetamine, is releasing dopamine. So here are the control subjects. When to these control subjects you give methylphenidate, dopamine receptors, they disappear because there is dopamine inside the brain to be spritzed away from the dopamine neuron. On the contrary, the placebo, methylphenidate, releases dopamine and displaces that binding of the radio marker. Okay? While the placebo doesn't do anything. Yeah, that's the concept that I got confused for a second. But that's the concept. In the control, you can demonstrate that there is dopamine inside. In the addict, you don't, in brief. Okay? Can I go? So in general, these dopamine D2 receptors are used as a proxy of addiction and are all reused in various addictions. So we can take this as a stepping stone to devise novel therapies. In general, the reward circuits in a non-drug abuser are working much more than reward circuits in drug abusers. Okay, and in general, it's not that the drug abuser doesn't perceive reward any longer, but he certainly puts the drug at the top of his rewards, and all the others, they come after that. Okay? This is the counter proof. I love this experiment. Thanos et al. Popper would probably like also this thing. What did I say so far? I said that an addicted brain has an hypofunctioning dopamine system. Thus, if I will have a system to potentiate the dopamine transmission, I should observe the opposite. No? Popper, falsification of data. If you are honest as a researcher, you must design not the experiments that are needed to support your theory, but the experiments that will destroy eventually your theory. Okay? And this is the experiment. What did they do? They injected dopamine D2 receptors in the nucleus accumbens of alcohol-dependent rats. Okay? So increasing this should, if I'm right, reduce alcohol administration, and this should correlate with the presence of the protein. And this is exactly what happens. Okay? The alcohol intake, as you inject the first injection of the vector, and alcohol intake reduces. Then you do the same thing the second time, and this is reversible. Okay? So I am fully persuaded that an addict has a lower functioning in its dopamine receptors. Let me say one thing important to conclude is not, okay, the dopamine has been my lover for so many years, but I'm not so obsessed with dopamine. So I'm talking about dopamine because I know, but that doesn't mean that there are other neurotransmitter systems important and involved in the process of drug addiction. Like CRF is one of the most important, glutamate, and we could talk for long about the various neurotransmitters involved. We can now use, yes?
The animals in that study, presumably they controlled for overall level of activity of the animals between the two groups.
The behavior in it?
Yeah.
I don't remember.
Because if you
But the paper is published.
You
This
have,
is Thanos paper.
if you
Long ago.
overactivate the D2 channel, then you're increasing activity in the indirect pathway of both behavior, which will
Yeah,
have an
you are
inhibitory
doing
effect
certainly many
on
things.
behavior.
Yeah.
So that might generally reduce behavior, of which alcohol self-administration will be one behavior which is less likely. But you might just be making it less likely.
I don't remember. I would bet that they did it, the behavioral analysis, but I don't remember. Should I go to the transcranial?
Yes.
Yeah.
Are we
Waiting
out
for
of
it.
time?
Yes.
That's what we're waiting for.
Yes,
I think,
we are.
Yeah, we are waiting for the transfer.
Okay,
That's why we're here.
let's go fast. I know. Me too.
Exactly.
Transcranial magnetic stimulation, what is this? It is, okay, by the Faraday's principle, if you take a wire and you pass high voltage current around the wire, as the current flows, will generate a electromagnetic field, okay? This electromagnetic field, why should we break our brain searching for an electromagnetic field instead of the electrical current normal? For a very important reason, because the electromagnetic field crosses the skull painlessly, okay? So you put this figure of 8 coil where the wire is inside, it generates the electromagnetic field, you stick it next to the prefrontal cortex, and the stimulus goes in, okay? It simply becomes a matter how deep this thing goes, okay? The initial studies were done in the motor cortex, and this is very persuasive, of course. No, if you don't believe it, you stick the coil on the motor strip, on the Rolando scissor, where you have the thumb, the homunculus. You remember the physiology books with that little monster with lips, huge, all that stuff? You stick the thing there, you increase the current, and at one point your thumb will flip. Flip, flip. Every time you give thing, it flips. We all know that the motor system is a 2-neuron system. The first motor neuron sits into the cortex, into the motor cortex, sends the axons down in the same hemisphere, then it crosses the pyramids, it contacts the second motor neuron, and it goes here. So that's the best proof to say this thing is working. Thanks to this demonstration, we have a tool that allows us to modulate brain activity in conscious, healthy subjects. No need for anesthesia, no need for hospital, no need for nothing. You need a machine, a transcranial magnetic stimulation, a researcher that knows what he's doing, otherwise you can roast your patient. But for the other things, is a very positive way to modulate brain activity. I'm putting this against the other ways we have. The other ways, as I was anticipating at the beginning, are drugs. Drugs, molecules. They cross the blood-brain barrier and they reach the brain. And in psychiatry, there is a terrible attitude to mix and to administer several molecules at the same time. This poses a big problem, that while the pharmacology of dopamine blockers is known, and the pharmacology of anxiolytics is known, and the pharmacology of antidepressants is known, what is not known is when you administer the three molecules together, and the individual loses cognitive ability. So this is an excellent reason to investigate an electrophysiological method, painless, virtually free of side effects, other than the fact that we must be careful in selecting patients because epilepsy prone, pacemakers and those things for eating. Huh?
Piercing.
Piercings, yes. Somebody has also said something about tattooing, which is not good, but anyway, we are in cosmetology here. So when I learned about this stuff, I thought I can employ this thing in attempting to stimulate a hypofunctioning dopamine system. This is a recent review by Diana and Michael Salim, and there are several important and useful informations here. Here, for instance, as compared to the skin surface, you see the capacity of the method to induce action potentials, okay? The strongest one is deep brain stimulation, the thing we were saying before, but remember, that electrode sits next to the cell body in an area, within an area, so it needs surgery. After that, we have TMS, H-coil, which is the coil that I use, H-coil, which is a bilateral coil. You are stimulating both cortexes together. With a figure of 8, you stimulate one cortex. One, asymmetric, either left or right or whatever, but one. And these two, they reach, H-coil goes deeper, TMS reaches certainly the cortical layer, okay? And through the cortex, depending where you are stimulating, you can reach distant areas. A final thing regards the direct current stimulation. This one, anode, cathode, and all this. There is a big limitation here, is the fact that current burns the skin of the patient. So you are limited in increasing your current, and in some cases you cannot reach a level sufficient for depolarization of the pyramidal nucleus. In other words, you are inducing an effect, but it is difficult to be persuaded and fully convinced that you are in effect inducing a depolarization of the biological structure under study. Here, this is a thing that is taken from a paper we published last year that conveys a few key information. So you stimulate in the point 1, but you can expect the effect in point 2. To the nucleus accumbens, thereby increasing dopamine release. And here is depicted better. You see they get thicker, and this thing increases, so it should increase. Oh, I'm sorry about that, but this is the data published already long ago by Antonio Strafella in Toronto and his own group, which has shown that stimulating with transcranial magnetic stimulation the prefrontal cortex allows you to measure and to increase dopamine release in several areas, not only in the ventral striatum, but cingulate cortex, orbitofrontal cortex. This is an example, we are all tired, and I can see that, of a paper we published last year. We are measuring here the DAT, the dopamine transporter, okay, with the cocaine analog. And this is PET, single photon tomography, whatever, okay? The alcoholics, they show more dopamine transporter than healthy controls. If you think this is also consistent with the lack of dopamine in the synaptic cleft. If there is more DAT, it will take away more dopamine, so the quantity of dopamine will probably be less. This is when you do the stimulation in the alcoholics. When you do the real stimulation, the DAT goes down after TMS. In the sham, nothing happens. Together with a reduction in the dopamine transporter amount, there is also a reduction in the alcohol intake during the month of TMS administration. Okay? This is another study that we published earlier. In cocaine addicts, there is a reduction both in treated and controls. And as I was saying, we were discussing earlier, there is a real possibility, in my modest opinion, that TMS represents, one, a useful tool, free of toxic drug-induced effects. Secondly, it needs to be evaluated carefully to, let's say, to further extend the already promising results that are appearing more and more in the literature. Please.
Are there already long-term follow-up? Like
No.
people that
No,
like in India?
not yet. We are all trying to do this. We are evaluating now long term. What do you mean by long term?
Well,
that's another key point.
Yeah, but like whether you have stimulated these people maybe 6 months later, that there's relapse or...
Here in this paper, you can find up to 9 months. Okay? Up to 9 months. And in 9 months, it seems that sham treated are taking more cocaine. Relapses are increasing. Remember that these are very few numbers. It's not easy. The people, when in a clinical work requires lots of patience, because they come and so you present the project, so you are a cocaine addict, you want to stop, I can propose you TMS. What is TMS? Oh, TMS, I will put a thing here. And no, I won't do it. No, you want to do me electroshock. And so it is not accepted easily. You see, it's difficult to recruit people. and then they drop out, and there are many difficulties. So the patients are very few, but that's what happens. And the rest is that we are collecting and collecting and collecting data to evaluate the long range, because we're hoping to take advantage of synaptic plasticity. Please.
What's the subjective experience of the TMS, for example, on controls? Is there a possibility that something could be addictive?
It could be addictive, the TMS itself. Yeah. You are absolutely right. This is one. Okay, the report are first anecdotal, because we question all the patients. So how do you feel? How's it going? You cocaine? And there are things that struck me. Two. One is, I remember cocaine. I didn't forget cocaine. But cocaine doesn't induce me the same effects seeing cocaine, only seeing, that I used to do. It's like looking at a picture of when I was younger. Okay, that's one frequent report, independent, which indicates some effect on the memory side. It's changing.
Is it, yeah.
Oh, addictive. You were saying that. Many people, when they stop treatment, they say, oh, gee, already finished? No, I want to come back. Why not? This is curious. They feel safe. The treatment and the setting and the physician and the machine, they feel safe. Not everybody, not everybody. Again, I said it's anecdotal. Some people does this, but these two reports, let's say, are the most common. The most common.
Conclusions?
I concluded already. Please.
No, now we switch to the question session.
Oh, now it begins.
It's all highly structured. No, it's yours.
No,
for
she
now.
wants to ask a question.
Okay, question.
What is the mechanism of TMS?
How does it work, TMS, right?
You can do.
See here? This is the coil. This figure of 8 coil. This is the most common coil. It's not the only one, but it's the most common today employed. The mechanism of action is that when you make current flowing inside a coil, the current flows here. See the black arrows there? See the black arrows? Do you see them? Yes, you do. Okay. Do you see the red spots going opposite, perpendicular? The black arrows is electric current. The red spots are electromagnetic fields. Okay? The electromagnetic field and the electric field, they go in parallel. The difference between the two is that the red stuff, so the electromagnetic field, is able to cross painlessly through the scalp. Okay? Are you following? Yes. So once you have the electromagnetic field within the scalp, which has with itself the electric field, you generate depolarization. It's like using an invisible electrode, okay? It's like electric at this point on, you have to think it as an E current. We call it in this paper E field. see what I'm saying? The proof is the motor threshold. The thing that I told you at the beginning. If you stimulate the motor strip and you increase the current, you will see your thumb twitching, contralateral thumb. Stimulate here, in the left cortex, you will see the right thumb twitching. You stimulate left cortex, this one will twitch. So you are transforming an electromagnetic field into an action potential, which now travels by virtue of the neural pathways. And as you can see schematically here, you can activate this one, which will go eventually to dopamine-containing neuron in the mesencephalon, or it can go to the contralateral cortex. Did I answer? Yes?
Well, we haven't really explained how you map the magnetic field back into the movement of ions, right? That would change the
Okay, there is people, you can look into Abraham Zangen work. In 2002 or 2003, they measured with a system called the phantom brain. The phantom brain is a fake head, okay, which has the conductivity similar to our skull and skin and hairs for those who have the hairs, some don't. Yeah? And then you fill this empty head with saline. Then you apply the stimulus and with a voltmeter, you measure in the various areas how. And they can map, and they mapped the distribution of the E field.
Okay.
Okay? This one here, I know is not, you see this? This one. This is depicting the stimulation that occurs in the brain. So, in the middle here, you have the maximum of stimulation. In the periphery, minimal. This is one of the main problems because the geometry of the coil will determine how large, three-dimensionally, the area of stimulation will become. Okay? But this is all work in progress. Please.
No, wait, we start from the
Yeah.
Related to this, but it's really, because we're comparing with optogenetics, like in the way you can...
It's an inspirational thing. It's
Yeah,
because-
So the question is, what's the spatial resolution? How many cells are you actually affecting?
No, we are affecting a pool of neurons.
Oh, look, you talk about the cubic centimeter, so I mean, it's a huge volume, right?
Yes, yeah, in those terms, cubic centimeters. That's rough measure, okay?
Okay, Dina? No, we start in the back, go for it. Dina.
He will do this, don't
Exactly.
ask me.
Dina's answer.
Really great talk. So,
You have to speak up, Dina, disco there, you know that.
So I was wondering, in regards to the stimulation thing, since we're stimulating the prefrontal areas, which are involved in a lot of things, including executive functions and so on, there's a chance that this behavior results as the reduction of the alcohol intake might be related just to improve cognitive function, right?
Yes.
Controlling better, you know you should do this. So is there a way to disentangle this?
No, not that I know, but there is a way to observe the cognitive effects. So there is already literature which suggests, for instance, in amnesic patients, initial Alzheimer's patients, their cognitive function improves, like various functions, like working memory, or it can be decision making, but there are already indications. This is a very young field, seen with skepticism by many, not only patients, even our colleagues. And don't forget that against this stuff, the big pharma is behind. So, it doesn't work. It cannot work. Yet, there are studies that are taking place not only in addiction. I would say that most of the activity goes in other areas, like depression, major depression. I don't know if you are aware, Alvaro Pascual-Leone and Daskalakis in Toronto and Bumi Zangen in Jerusalem. I mean, there are many people that are working actively and intensely. And the FDA has granted the permission for depression, even to the machine of Zangen, and they are now applying for addiction, because addiction is another emerging field. But in general, the field is very young. The paper that is credited as being the first one to open the thing is 1985, I think, Barker, in the motor cortex. And there are many studies in the motor cortex.
Jordan?
Going back to the hypodopaminergic theory, do you think, or is there evidence that it also applies to addiction, to things that are not drug?
Behavioral addictions.
Exactly, like addiction to game or addiction to
Food.
food, for example, or things like that.
I think it does. Nora Volkov has published a beautiful review, I think it was December 2017, about the food addiction. She calls the dopamine system the dopamine motive system now. So if you're asking my personal opinion, I think yes. The hypodopaminergic state applies not only to amphetamines or psychostimulants or alcohol or tobacco or the classical drugs, but it also applies to what we call behavioral addictions, which is internet gambling, for instance, internet dependence, pathological gambling, including food addiction.
At which point do you think it would apply also to obsession? In the sense of...
I don't know. I don't know, because if we enter the psychiatry sphere, psychiatry is the most esoteric part of the whole medicine. You know, it's simply difficult to discriminate between impulsion and compulsion. And every clinician makes his own in that. And it complicates things when he administers drugs. The standard drug cocktail administered to a cocaine-dependent individual nowadays in the Western world, no, I'm not talking in Papua, I'm talking about Europe, United States, Japan. The standard cocktail is an anxiolytic, an antidepressant, and a mood stabilizer. It gets these three things like that. Standard. These three molecules, he has to deal with that. You see? So I don't know. In addiction, and also in addiction, you have to, first of all, to establish if the individual is dependent or is not dependent. And eventually, if he has other pathologies. And I go back here to the advantages of this thing. At least this one is not inducing toxic effects. Perhaps it won't work, okay? Perhaps it won't work. But it will not smash your brain with things modulating GABA, glutamate, dopamine, serotonin, noradrenaline, and all the things that happens when you administer those drugs.
Please, go ahead.
En el proyecto piloto que tienen de la cocaína, por ejemplo, en el caso de Parkinson, aparte de la electroestimulación magnética, se les hace un feedback. ¿Habéis pensado en el feedback que van a hacer o si lo piensan poner o cómo piensan hacer ejecutar?
I'm afraid that couldn't
Well, if I get it, I think she's saying, how are you going to use this in the real world in the end? How are you going to use it as a therapeutic intervention?
¿Qué entiendes para feedback?
Neurofeedback como un programa adicional para que ver si está como complemento a la estimulación.
Neurofeedback.
I don't know. In our addicts, which are cocaine, alcohol increasing, tobacco increasing, we have a protocol for TMS accompanied by psychological support, CBT. It's called cognitive behavioral therapy. This is all I know. This is, don't take me to the Parkinson's field. Oh, yes, yes.
But you have to also explain, of course, why you believe neurofeedback would actually contribute. Why do you think neurofeedback would be a useful addition?
In Spanish, please.
Maybe at lunchtime there is another
Okay.
question.
All right. It's open and we can discuss this later.
Yeah.
Okay.
Okay, I was curious about this device. Yeah, that's okay, and how it works actually. So it's creating an electromagnetic field. It's okay. So it's stimulating the current inside the brain, so the neural activity, and
It's generating a current
it's generating a current.
within the brain. This one. This is within the brain.
Mhm.
It is carried by this, by the electromagnetic field.
Perfect.
So in brief, ions will move and will depolarize your.
Marco, there's a problem. I think this question is contagious because you posed the
Yes,
same question, right?
yes. It's
It's
contagious.
Your neighbor just posed the same question.
We were talking about this and wondering how you can actually change the structure of the brain somehow to target the dopamine system. I mean, because you are,
Okay,
I guess you
good.
are involved in all
One question at a
electrical activity
time.
there.
One question at a time. I will provide as much as I can all the answers. Is the question related to the fact that you are skeptical about the mechanism of action?
No, Marco, I think I got it. He wants to figure out how you reach in the nucleus accumbens and VTA.
Oh, that's the second part.
If you stimulate the surface. I think this is their key question now.
I show you.
Yes.
Okay, thank you.
Let me go. No. I showed you this here. And I also showed you the structure. This is a drawing, but it is a realistic drawing. Cortex, cortical mantle is a 6 layers thing. Okay? There are two types of pyramidal neurons. Second layer, it gets stuff from outside. The afferents to the cortex, any cortex, barrel cortex, occipital cortex, motor cortex, axons, they come here. The input comes here. The one in the 5th layer is the output neuron. Okay, between these two, there are a bunch of interneurons, GABA stuff, blah, 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 blah. Okay? All right. You apply the stimulus, you aim in several places. Among these is the dopamine neuron in the VTA. Okay? So the drawing is here. Pyramidal neuron, dopamine containing neuron. This one, this guy here, is carrying glutamate. So when he fires, he spritzes glutamate. If there is dopamine, dopamine does burst firing. This is known, it's unknown. I can give you all the references, anatomical and electrophysiological. Okay?
No, we're talking from dorsolateral frontal cortex to VTA. We're driving the dopamine neurons over
Exactly.
layer 5 pyramids.
So
and now we're talking to the accumbens.
We are talking to the accumbens. Once you spritz glutamate into the dopamine neuron, it will increase its firing. It will switch from single spiking to burst firing is called. Dopamine neurons, they fire in two normal modes. One is single spiking, and she does pop, 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 pop. And then burst firing, See? This second mode is way more efficacious in releasing the transmitter. And we know that is dependent on glutamate arriving from cortex. From classical studies, Gariano, Anna knows those. Okay, I'm talking about 88, something like this. You stimulate the dorsolateral prefrontal cortex, you record the dopamine neuron, you blip here, and she goes. Blip, pop. See? Okay. Once you have stimulated the dopamine neuron will spritz dopamine into the nucleus accumbens. Correct? Correct?
Okay.
Okay. And here, this is humans. So TMS is increasing dopamine release in this one that you cannot see, but go is Trafella 2003 and 2001. You will see it with PET scan. TMS and less dopamine receptors because dopamine is displacing the radio tracer. Persuaded?
Thank you very much.
Sure.
Okay, Giovanni.
My son like a detail, but at what frequency are you stimulating?
You know, 10 Hertz, 1 Hertz as a control, and we are now doing theta burst.
Exactly. Do you think that theta burst might be the most effective for some reason?
Theta burst is very sexy.
So
I cannot resist theta burst.
exactly, me neither. That's why I'm asking you that.
You want to see the theta burst paradigm?
Do it, yeah, sure.
Sure. He wants to see it because I said that it's sexy.
Is that something really sexy?
I need simple messages, Marco. Not all this neuro babble stuff.
Right.
Just say, this is the greatest, this is sexy, okay, I'll pay attention for 10 seconds.
He's a simple neuron.
Exactly.
This is very intense to bring in this up because this is very important and it goes deeper into the importance of stimulation protocols. The frequency is one of the key aspects. So you have single pulse TMS. Single pulse TMS is the one that is used for motor threshold. You simply apply one pulse, you see the tongue switching, you determine 80% of the power of your machine, and that's it. If you go to measure things after a single pulse, you won't see anything, okay? From now on, you have 1 Hertz, 10 Hertz, 15 Hertz, 20 Hertz, 25 Hertz. These are limited by the safety rules. You cannot apply 100 Hertz, for instance. LTP in rodents is done with 100 Hertz. In a human being, I cannot do it
In
simple.
deep brain stimulation, you can though. In
What's
deep
up?
brain stimulation, you go easy to
In
100
deep
hertz.
brain stimulation, you can, exactly. So, this is repetitive, and this is called pattern, okay? As you can see, this is theta bars. It can be continuous, or it can be intermittent. As a first approximation, continuous is considered to be inhibitory of the system, okay? Whatever system. Why is this? Here is plenty of good physiologists. Why could this be? But a possibility, a simple possibility, is that the neuron is going into depolarization block.
Yeah.
It goes into depolarization block, and then it doesn't work anymore. On the contrary, intermittent, and you see how it goes. For 2 seconds, it stimulates with triplets at 50 Hz. It goes 50 in the first 2 seconds, then 8 seconds silence, and then it keeps going for 3 minutes, I think. Using this, John Rockwell in London and one, I don't recall his co-workers, they have shown an excitatory effect on the motor evoked potential. Okay? So here, this is intermediate. Of course, these initial ideas are giving, fueling newer proposals, newer possibilities. And we discussed some of these in the 2017 paper. There are quadruplets. You can do several things. You can play as you play with your neuron in a rodent brain.
Sorry, I don't want to be pedantic.
No, you're not.
Well, not yet.
Not yet.
Not yet.
Okay,
Yeah, you
Let's be
decide.
cautious, right?
So I understand a bit about this kind of stuff. But do you think this specific like frequency has any relationship with like the possible functional role of oscillations in the brain? So like, one of the reasons why I'm asking this is because like, for example, in frontal cortex, you see like very strong signatures of deep oscillations during cognitive control. Now, I'm wondering, if you stimulate with TMS in theta bursts, are you somehow eliciting a type of like executive function activity?
Or
Like-
blocking, possibly.
Huh?
Right? Or blocking, you could have.
Beautiful. The possibility is beautiful, but
Theta frequency is simply the resonant frequency of pyramidal cells, centers on theta. So you are simply providing more efficient stimulation of pyramidal cells by hitting them at their resonant frequency. The resonant frequency of inhibitory interneurons is in the gamma range. Okay, so it's rather simple. You are simply optimizing the driving of pyramidal cells. That would be my explanation.
see?